Hello, my name is Jackowski. I'll be talking to you about the Thermal Subsystem on behalf of my colleagues Joseph Velasco, Joseph Binder, Robert Hawkins, and Joseph Palomares, who will also be talking to you shortly about the Thermal Subsystem. Next slide, please. The main requirements for the Thermal Subsystem are to maintain all component temperatures during all phases of the mission, and also to meet this requirement with 1 heat pipe loss as stated in the RFP. We also set an internal requirement on ourselves that any analysis that we would perform would have to use an 11 degrees Celsius margin within the predicted to the operational temperature range that we want. So you can see here in the plot to my right some of the more stringent component temperature ranges. The most problematic ones included the oxidizer tank on the orbiter vehicle, as well as the batteries on all of the vehicles and the instruments on the orbiter vehicle. Next slide, please.
You got flight predicts, so are these the temperature predicts of the boxes themselves, or is that in the flight?
No, these are the component specifications. So these are the requirements from the technical directions.
So that's the, I would say, the operating ranges.
Yes, they're operating.
And your last line says you're going to be 11 degrees inside those operating ranges?
Yes.
So your flight
with our margin. So basically, we're saying that our analysis, we're not 100% sure that our analysis is completely accurate. So we want to apply an 11-degree margin on our analysis.
So did you supply the next higher level margins to your test community? Flight plus 11. Your predict plus 11 gets you to flight, and another 5 degrees you get the ATP.
So they would have to qualify past these ranges, I suppose. I think INT might be able to answer that later.
Please repeat the question, I couldn't hear it.
Just wanted to know, was there an additional margin above 11 for acceptance and qualification?
Yes, later in the presentation we will do thermal vac testing, and in that time we will go 5 degrees Celsius above and below the expected temperature environment we plan to see from analysis.
For acceptance or quality?
We will be protocoling our components, and then at the system level, and we are going to be assuming that all flight hardware will come in protocol. I will go into more detail about this in my presentation.
Thank you.
And where did the 5 degree number come from?
That is from a mill standard, 1540.
Yes, that's correct. Next slide, please. These are some of the environments and load cases that our vehicles will see. The orbiter sees the greatest variation in a solar heating environment, as does a flyby of Venus, and then does a couple of Earth flybys, and then a flyby of Saturn. So you can see that the flux of Venus is very high, around 2,600 watts per meter squared, and the flux at Uranus is very low and almost effectively non-existent at only 4 watts per meter squared. So we looked at some of our flyby cases and to see how much albedo and IR heat we were getting as we passed by the planets. A couple of them were pretty significant. You can see in this plot to the right the flux over time on various panels of the spacecraft above the Venus and first there's flyby albedo heat, which were the most extreme, so that's just an example. Next slide, please.
I'm sorry, I hate to bug you a little bit.
Yeah.
But why is the flux large? It's larger in one situation over there than the flux.
Okay, let me explain the plot a little better. So those are average over time, so you can see there's a duration there. So I pretty much took the total. Yeah, it's total over time. And those are different sides of the spacecraft, so we assume that the spacecraft was 6 flat plates, basically, used flat plate factors. Come up with those numbers.
Okay.
Thanks. So our analysis, we initially performed an analysis using basic steady-state energy balance type of things, and we wanted to go more in detail and figure out how exactly our temperature gradients across the spacecraft were. So we decided to do a finite elements analysis, and we created models in the MSC Patran and then solved them in SIMD-G, which is a finite difference solver. So here's an example of some of the meshes we created. No questions? Okay, so a brief overview of the orbiter design. It's a fairly challenging design because the vehicle is very large and has a fairly low electronics density. It's got a lot of paneling and a lot of surface area, so it's radiating out a lot of heat. If you covered in MLI blankets. There's quite a significant heat through all those. So we have a pretty low amount of waste heat, and staying warm is in general much more problematic than keeping cold, even during the heatest case. And to account for many of the huge environmental variations, we use things such as louvers. And we also have our thermal skirt, which will be pointing at the sun when within 1A view of the sun. Next slide, please. So here's a table of some of our components, MLI, and interfaces we'll be using on the spacecraft. So basically, we're using 3 different types of MLI all around the spacecraft. We have thicker blankets on the outside. For most of the spacecraft, we're using a 20-layer gold-ized capped-on outer cover. And on the thermal skirt, we wanted a lower absorptivity, so we're using a Teflon-coated outer cover. And we weren't sure exactly how to account for the degradation of this absorptivity and an interplanetary mission, since most of the data out there was more out of Geo or Leo. So we kind of went with more of the worst case. So the absorptivity starts at 0.1, we use at 0.3 for the thermal skirt. So for many of the higher power dissipating components, we decided to paint them black and let them radiate mostly internally, and we applied silicone RTVs to the interface between the component and the spacecraft panel to try and get better conduction. A few of the components, such as the batteries, are covered in MLI internally. The propellant tanks and pressure tanks are also covered in MLI internally to try and retain heat. And the batteries also have titanium standoffs. One concern was the tweeters, which have a very high watt per area dissipation on their conduction path. So we decided to use aluminum doublers to try and spread the heat out better. Heat pipes probably would have been a bit of overkill, since we don't want to spread out heat too much when it is. If there are no questions, we can move on.
We've also accounted for the micrometeorite
Yes, so the survivability subsystem, or not really subsystem, but the survivability of the team has decided to put, I believe it's Kevlar and Nextel inserts in pretty much all the external MLI blankets. Slide, please. So we're using 90 watts of total heat.
I'm sorry, your TWTAs or your TWTs at the very least, you can have those as exterior mounted on your spacecraft to radiate separately. Did you look at those?
Right, yeah. So basically the deal with those is the communication subsystem wanted them as close as possible to the feed horn to try and reduce the amount of traveling wave, to reduce the amount of feedbacks and waveguides. And they really weren't getting too properly found, so it wasn't really too much of a problem. There aren't really many electronics mounted at that part of the spacecraft. We tried to group all the instruments together on the instrument panels to see how similar requirements. And we tried to group as many things as possible, generally, as much as mass properties would allow us. We're trying to convert some.
Yeah. Next time, tell the comm guys to man up, because the thermal problem is way worse than the comm problem.
Can you hear that, Jay? Okay, next slide. Oh, no. So you can see we have our biggest power draws for heater power are the propulsion system. We have the reaction wheels actually get pretty cold when they're in their low power states, since they're all the way at the top of the spacecraft and nothing else is really up there. So those require about 25 watts of heater power spread over the flat wheels. And in addition, power basically, since we're limited on the amount of ASRGs, they basically cut us off at 90 watts, and everything above that we try to make up with radioisotope heater units. These are small little casings of plutonium. They have about 1.4 ounces of plutonium, and they weigh 40 grams total, so they're pretty light. Well, not total, but we're using a total of 95 of them, 55 on the instrument panel to try and keep that area warm. 34 more near the top of the spacecraft by the reaction wheels, and 6 more by the ion wheels. So, other questions? Sure.
So there's only 30 of them available in the world.
30 RHUs. Is that?
They're out of the country.
Well, our customer said that they provide
found a good supply.
Oh, you don't know about that.
However, we did figure it would be better to, instead of add, say, another ASRG which has significantly more plutonium, it'd be better to add smaller chunks of plutonium exactly where we need it. So,
Did you consider the fact that the ASRGs are 22% efficient or whatever the number is? So they've got a lot of waste heat that are radiating out the side.
yeah.
So
So
bring some of that inside and use it.
Yeah, we initially had heat pipes going from our ASRGs to the spacecraft, but in our simulations, they weren't running, it's hard to say how accurate our simulations are, I guess, exactly, but our predicted external surface area, like average surface area, wasn't too high, so it wasn't pumping very much. And they are radiating through the spacecraft, though we painted most of the interior black to try and get as much of that as possible. It won't be so much.
There's over a kilowatt of power there that's available to be routed around. You certainly can go up with that.
All right, maybe we'll try and do something
Or
more.
you have to think about where you're gonna install.
Well, it turns out that right now they're installing them on the outside panel.
I don't mean on the spacecraft, I mean the site.
Oh, you're required to install them on the launch pad.
Right, so.
But just like the MSL, they just have the heat pipe system sitting there waiting and then bolted up.
Just like that.
Easy to do. Anyway, it's a lot of power. It's great, very useful stuff.
Next slide,
Just
please.
clarify for what you said, what's
Sure.
always on? The unit's always on or the heater?
The unit is always on.
You guys said earlier that the IMU was not only on some portion of it.
That's incorrect. One IMU is always on.
And I'm sorry, where did you get the power number for your tanks? The 30 watts, did that come out of your simulation?
Yes.
Really huge tanks, that's not very much power.
So the MMH doesn't need any power. Yeah, because it has a range of down to minus 56 around it. So that wasn't really a concern at all. That was a big driving factor for why we went with MMH as opposed to more traditional hydrogen. Next slide, please.
You know the TWTs, they're always used to be
They're always
GPCs are always active, always on in some grassy state.
they're always on in a 25% standby mode for reliability purposes.
Okay.
So that's 48 watts of thermal. Next slide, please. Oh, okay. So the radiators and movers we'll be using, we tried to minimize the amount of radiator area in general, since we're very cold to hear this. We have, the primary concern was the oxidizer tank overheating, since it can only get to about 21 degrees C. So we have a pretty large louver located beneath the messenger magnet, or the magnetometer loom, which is 0.5, half a square meter. And it's not coupled directly to any electronics, but its general purpose is to reduce the bulk temperature when we're near Venus to try and get the oxidizer tank a little bit cooler. We employed 2 more louver's on the ACUs and the main PDU in order to also try and dissipate some of its energy externally, as opposed to letting it go internally and letting it get the oxidizer tank.
See,
In
I know
addition,
you're trying to speed up, but I'm gonna make you slow down. So your emissivity, though, you're in a really long orbit. So if you're expecting that 0.9 to stay at 0.9, that's not gonna happen.
okay.
So I'm just saying, if you
Right, yeah.
need it to be 0.9, you're gonna have to do something else.
I've never seen many end-of-life emissivity values. From what I understood, it was mostly objectivity, but I'll look into it some more.
Same for
But
that.
your A over E is what's important, right?
Right.
Or your
Right.
alpha over epsilon, sorry.
If we're not getting much sun at,
But you have a large period of time where you're very close to the sun.
yes, but we're pointing in a certain way. So none of those radiator panels will see the sun when we're in our worst environment.
Unless bad stuff happens.
Right, and I've run simulations to see what would happen, and if we are hit by the sun, we're spinning around by about 1 oscillation per day. I'm not sure how realistic that is. It would hit, the instrument panel would get to about 40 C in 100 hours, and it would kind of start to fluctuate like that. So it would definitely be a problem. We'd be in our upper range. So one other problem we had is that we didn't have very much detailed information on the thermal control systems that the instruments actually have, because a lot of them do have radiators and they have their own entire systems and the information is for them. Next slide, please. Okay, so here are our results. You can see the results of the steady-state pattern simulations and all of our wattage applied. Basically, we stay within 11 degree margin. Both of our spacecraft stay between minus 40 and 20. So some parts get really cold. Some panels on the far side where there's no electronics. Next slide, please. To my right, we have a video of our transit from, so now we're going from Earth to Venus, and it heats up and peaks, and we go to our second Earth flyby, where it heats up again, and then we move further away from the sun, so it starts to cool, and then back towards the Earth, where we get our final last heating peak, and you can also see, there's our last flyby of the Earth, and now it's going to go around again. So you can see these results also in the platform over here for a few components. The average instrument panel temperature and the oxidizer tank and batteries. This is with proportional heater control applied. And we're still meeting 11-degree margins, so we're fine there. And so this is with all the albedo and IR that I talked about in the beginning. If there's no more questions, I'm going to hand it off to Joseph Palomares to talk about the UPS and probe thermal control systems.